In this video, we are solving this system of equations over the integers. And that means that a and b are both integers, and we're trying to find a and b. Try to pause this video if you can and try to solve it, and you can go through the video and see if you got the correct idea. Okay, so let's try to break down this a cubed minus b cubed. So let's try to factorize that. A nice guess would be a minus b times a squared minus b squared. But if we factorize this, we'll get a cubed minus ab squared minus ba squared plus b cubed. So quickly, we notice some problems. This is supposed to be a negative, and we're not supposed to have these terms. So let's see. A minus b times a squared. Let's do, let's do plus b squared, because that would make a negative here. Okay, so now if we expand that, we'll get a cubed plus ab squared minus ba squared minus b cubed. So this problem over here was fixed, because now the b cubed is negative. But what about these terms? We still have to get rid of those. So let's try to factorize those. That would be, well, we notice the factor of ab. So if we factor out ab, we'll get ab times b minus a. Now that's interesting. We do not want that factor. So we want to add. So our answer would be a minus b times a squared plus b squared. And then we want to add in the reverse of that to get rid of it. So that would be ab times a minus b. Because if we add that in, that'll cancel out with our existing terms to make it 0. So we can factorize this. It's just a minus b times a squared plus ab plus b squared. And we can check that this equals a cubed minus b cubed. So that's our factorization. Using that similar method, after this video, try to discover what the factorization for a cubed plus b cubed might be. Here's a hint. Try to write it as a plus b times a squared plus b squared, like we did at the start. And then try to get it so that you need to fix some terms and then factorize those terms and then combine it all together. So let's apply that to this problem. We know that this is just a minus b times a squared plus ab plus b squared. That's 49322. But we can plug this in. So then we'll get 26 times a squared plus ab plus b squared is equal to 49322. And we can divide, so then we get a squared plus ab plus b squared. And if we do some long division or whatever, we'll get 1897. And also, we know that this is true. So we want to somehow combine these two equations. Let's square this one to see if we can get something like the first one. We'll get a squared minus 2ab plus b squared is equal to 676. And so we also have a squared plus ab plus b squared equals to 1897. Let's subtract these equations. We'll get 3ab is equal to 1221. So then ab is 407. If we prime factorize 407, we'll get it's 11 times 37. So there's two options for a and b. It's 1 times 407, which does not work, or 11 times 37, which does work. So our answer is a and b are 37 and 11. So this strategy of using difference of squares to factorize a cubed minus b cubed is extremely helpful, because then we can get something simpler than dealing with cubes, and then we can just manipulate the two equations to solve the problem. Notice that something that was really helpful was that it was over the integers. Because when we got AB is 407, the problem probably still would have worked even if we hadn't been given that there were integers, but it might have been slightly harder because you can't immediately tell that this prime factorizes at 11 times 37. So here's an extension problem using this formula that would be for you to practice so that when this problem comes up on a competition, you won't miss it and you'll get the point. So let's just say that instead of A and B, there are X and Y, and X plus Y, X cubed plus Y cubed is, let's say, 1,300. Also, let's say that X squared plus XY, actually, let's do X squared minus XY plus Y squared. Let's let that be 65. And assuming this was possible, you're trying to find X plus Y. So this is the question, and I'll probably discuss it later in a different video. That's it for this video. See you next time.